Okay, lecture 19. So same as lecture 18, I'm going to give you a whole set of formulas and names, but of binary molecular compounds. So you should know those terms there. So let's get right into it. Carbon monoxide. Now this is CO, one oxygen, mono, one carbon, but we don't do monocarbon monoxide. What we do is, to simplify things, if it just says the name, then we assume there's just one. If there were two carbons, we'd have to call it dicarbon. But if there's just one leading carbon, then we don't put the mono in front of it. But we use the prefixes 2 through 10 for the first one, and then all of them for the second. So we always use that mono. So we have carbon monoxide. The formula, here we have one carbon, so it's not monocarbon, we just say carbon. There's two oxygens, so dioxide. So these are molecular compounds, so we have to use the prefixes. We don't use them in the ionic compounds. But here, we can see that we have two compounds that contain carbon and oxygen. The only way to distinguish them is by the relative number. Okay, the formula for dinitrogen tetroxide. So this is pretty easy once you get the hang of it. Nitrogen, it's di, so that's 2. Oxygen, tetra, know that that's 4. It's not quadra, it's tetra. Formula for PBr3. So this is phosphorus. And just like the ionic compounds, we give the full name first, and then we change the second part. It's not an ionic compound here. It's not. So this isn't an anion. It's just the ending, but we change it to tri-bromide. The formula for ammonia. Now, this is NH3. We don't call it nitrogen trihydride because ammonia was a compound that was known for centuries before they came up with the standard IUPAC naming system. So some of these names just stick, like this next one. This is water, H2O. We don't call it dihydrogen oxide, we call it water, because water was one of the first things ever named. So everyone knew what water was long before they knew it was made of hydrogen and oxygen. So its name has stuck, and you'll see it in the literature that way. When people are studying H2O, they're studying water or water vapor. They don't give it the fancy IUPAC name. The formula for chlorine monofluoride, so ClF. There's one fluorine, one chlorine. Chlorine comes first. The formula for SF6. 6 is hexa, so this is sulfur, hexa, fluoride. Don't forget the U. The formula for tetraphosphorus, that's a 4, trisulfide, so P4S3. And then N2O, so this is dinitrogen monoxide. And it's also called nitrous oxide, but we'll go with the name, the standard name, dinitrogen monoxide. If you know some of these compounds from a different course where they used the common names, that's fine as long as they're accepted common names. You can use those on my exam. The formula for decachlorine nonafluoride, so 10 and 9, so Cl10F9. So some of these I'm not sure if they actually exist. As a theoretician, I know that you can always create any of these compounds, even if they only last for microseconds in a vacuum. You can certainly create them, but the nomenclature rules apply no matter what the formula is, as long as it makes some sort of sense, and it definitely does here. We know the names, we know the numbers here, so we can go back and forth. The formula for, okay, so we have penta, arsenic, hepta, so this is all one name, heptabromide, and this is all one word, and then there's a space in between. The formula for heptaselenium octadiode, so selenium here, and then iodide 8, and selenium, because it is a non-metal, could could definitely be put in this form where it would be part of a molecular compound, even though it's also been used as in an ionic compound, just like oxygen. The formula for ClO2, so there'd be chlorine dioxide, then carbon disulfide, CS2. Formula, this didn't miss this one, so it'd be, those are subscripts, sorry about that. Now, when you see hydrogens out front, that generally means that it's an acid. So we wouldn't call this dihydrogen carbonate, this is carbonic acid. So the naming changes. We take the carbonate and we change it to to either OUS or IC. In this case, there's only IC for the carbon or the acid with a central atom of carbon. So this is carbonic acid. Nitrous acid is HNO2. Nitric acid is HNO3. So there is a pattern to it. Sometimes it's a little bit vague and goes back many decades or centuries of where they came up with these the naming system. But and here it is. HNO3 would be nitric acid. Generally, if you have a central atom in an acid and there's more than one oxygen, the one with the lesser oxygen would be OUS, and the one with more oxygens, IC. And it can get even a little trickier than that, as we'll see. Looks like I have them down here below. Phosphoric acid, H3PO4, and then H2, and then phosphorus acid would be H3PO3. But this is the correct one here. Formula for H2SO3, this would be sulfur. This is the sulfite, and it changes to sulfurous acid. So the ite changes to OUS, and the 8, phosphate, changes to IC. Then we have sulfuric acid, so that is H2SO4. Then we have the formula for HClO. This is hypochlorous ion, so this would be this is the hypochlorite ion, so this would be the hypochlorous acid. Check something real quick. Okay, and then the formula for chlorous acid, comes from the chlorite ion, so this would be HClO2. HClO3 is going to be our chloric acid, and then our perchloric acid is going to have the most oxygen, so HClO4. I'm going to write it again here. And that covers all of the oxo acids. Then a couple of last things here. We have the hydrates. So with the copper 2 sulfate, we should be able to name that, or to write the formula. It's that. When it says pentahydrate, you have a hydrate. That means water is bonded very weakly to the ionic compound. It's not like water in a sponge where you can soak up a little or a lot. The water, and it goes wherever there are holes in the sponge. The hydrates, the water goes right to certain ions, and the water goes around the ionic the ions in the ionic compound in a set number. So copper 2 sulfate pentahydrate. For every mole of copper 2 sulfate, you'll have 5 waters, I should say. So that dot indicates it's a weak bond. So it's not just a physical effect where you're absorbing water. It's actually chemically there. So the formula, I guess that's the best place to put it, because it wouldn't have room otherwise. Then we have strontium sulfate heptahydrate. So this would be strontium sulfate. So the first part should be pretty easy, and then you see that we have water there, so it's got to be a hydrate. You look at 7, that's heptahydrate. So you can see it's one name, and then the second, and then the third. And there's spaces in between. The formula, now, I left this off when we were talking about acids earlier, but I put these on. I'll do another one here, but formula for hydrogen bromide. Now, hydrogen has only one electron, so it can only bond once. So we don't put a mono in front of the hydrogen, because that's the rule. But we don't put a mono in front of the bromine because there's no, or the bromide, because it can only bond once. So this is HBr. So even though there's only one bromine, we know that there's only one because hydrogen can only bond once. Carbon can bond more than once. Nitrogen can bond more than once. So we have to put in the prefix. But here there's no reason to, because we know that hydrogen can only bond to one other thing. So there can only be one other atom attached to the hydrogen in this form. Now it's not, it's hydrogen bromide, so that's going to be G for gas. When the gas is then dissolved in water to make it HBr aqueous, then it becomes something else. It becomes hydrobromic acid. Now it's an acid. So this phase, unlike the rest of them that we've done, the phase hasn't been important. It's the same whether it is in whatever phase form it's in, whether it's dissolved or it's a gas or a liquid, it's always the same thing. But here, hydrogen bromide, when we say that, we mean the gas. When its part is dissolved in liquid, then it is now an acid. Same thing here. This is HCl gas. That's hydrogen chloride. HCl aqueous is hydrochloric acid. Two different things. These halogen, same thing goes for HI and HF. We have hydrogen iodide and hydroiodic acid, hydrogen fluoride, and hydrofluoric acid. I won't write the rest of them out, they're in the book. But all of these halogen acids love dissolving water, and they stay in there. We can get 12 molar HCl. That's a very high concentration, and the gas will stay in there and act as an acid.